All right, guys. Oh, one thing I wanted to mention, I think I mentioned it in our announcements. If I did not, yeah, there's an express version of Visual Studio which you can download without even getting into DreamSpark. I believe I have a link to it in my file here. I have tried it now and it worked fine, so you can download it and install that, and you can just bypass, using Microsoft Store entirely. When you go to the page, it says this won't be updated past 2017, but that's new enough for us. Yes, sir. Oh, no problem. So, if you haven't already installed it, you might try that. I don't have a reason to recommend one over the other. Well, if you're going to go on and do C# development and stuff like that, take C# over the fall, you might want to get the full version of it. So the last thing we needed to hit, procedural programming versus object-oriented programming. If you've taken Java, if you've taken Python, you've already done some object-oriented programming, or at least use objects. Java is all about the objects. So if you've taken Java, you absolutely already know what object-oriented programming is. If you took 1113 and you use the class keyword, then you hit object-oriented programming, but not a lot of it. But if you use the turtle class, then that is an object, that is a class, right? You created a turtle and you were able to, move it forward, turn it to the left, turn it to the right. You had an object, which is data, and methods, which are functions that are attached to it so that you can control it. And there are other classes as well, a great many other classes. But mostly what we taught in Python was procedural programming. What is procedural programming? It essentially is just top down, right? It starts running the first thing, or in our case, it'll go to main and start running it, and then you can call some functions, and it kind of bounces around in the functions and comes back, and it has loops and if statements, and then you're done. But with object-oriented programming, you're thinking of it in terms of collections of data and ways to manipulate the data. Like, I want a patient, so I'm going to create a new patient record. And for that patient, I'm going to give it a name, and I'm going to give that patient, current weight and a birth date and a current address, all that kind of information, and then I'm going to save that. And so you'd create a new patient, patient equals new patient, that kind of thing, and then patient.name equals Joe, patient.date of birth equals whatever, and then patient.save to write it out to the file. So it's the way of thinking about things as in terms of collections of data, thinking about them as almost real-world objects. I have a patient. I'm going to change his name. I'm going to change, her birth date, that kind of thing. So we'll be hitting that not as soon as I like, not the way you would in a Java course, but I'm going to try to introduce it before we actually get to the chapter on object-oriented programming, because it's one of those things that I think we ought to hit a little bit earlier than I have been in the past. There's a version of the book, that has got the same title, but then in parentheses it says objects earlier or something like that, and it introduces the idea of classes, 1 or 2 chapters earlier. So the parts of a C++ program. I'm pretty sure we've already made a C++ program. We may as well crank up Visual Studio and make another one as we talk about the parts of it. So if you don't have Visual Studio loaded, which you may as well do every time you walk in here, go to the start box, type Visual, launch it. You may as well pin it to the dock, to the taskbar. Called it a dock. That's my Mac background peeking in. And then do File, New Project. What's today's date? June 6. So I'm going to give it a project name of June 6. I want it to be a C++ empty project. And it says something already exists called June 6 because of the last class I taught, so I'm going to call it June 6 CPP for C++. You don't have to do that. June 6. And then I'm going to come over to source files in my Solution Explorer. I did start the guy, did I know? Yes. If you don't see the Solution Explorer, you can always pop it back up under the View menu. View Solution Explorer. Right-click on source files and do Add New Item. Choose CPP, give it a better name than source.cpp, like June6.cpp. Hey, that's my birthday. Happy birthday to me. Alrighty, so click Add, and now we have our empty file. We're going to be putting our boilerplate in there. And I really should put the boilerplate in a notepad and then just copy and paste it whenever I want. Commands include IOStream, using namespace, std, int main, in parentheses, system parentheses pause, or system parentheses quote pause. It's only for the Windows users. And then return 0. And I'm going to add a cout command just so that it does something other than display something. Hi. How about that? \n end quote. Above that, I would put my name and the date and other useful information about the program, like the purpose of the program. So I should go and add comments to that effect. Name, date, Chapter 2, C++ programming, June. Yeah, we've already got the date. All right, so that's about the simplest program we can write. We could leave out the system pause, but then it would close so fast we wouldn't be able to see it. So I'm going to rebuild it, build, rebuild June, rebuild solution. And by the way, some folks were running it and not seeing the error list. If that is the case, I haven't quite figured out. Surely there's a way to bring that back. Maybe it's under the View menu. Okay, it just recreated it. And so when you were running it and not seeing the error list, well, you can go to the output. It's not quite as easy, but it does tell you the line number of the error right there, right? You see the build output, June6.cpp. It's not as convenient as going to the error list and double clicking on the top one, but it is there. And so then you can just go to line number 11. How do I find line number 11? You enable line numbers, as we've talked about previously, or you just scroll your cursor up and down, watching the line number appear there. All right, and why is this underlined? I don't know if you noticed the change that I made in order to break the code, but why is that wrong? Spelled correctly. The error is not, it says syntax error missing a semicolon. But I have a semicolon. But that is actually the error. What's the problem? Right, it's not on the line above it, Pretty much every line except ones before a curly brace needs a semicolon. That would be an error because it's before a curly brace. But all the other ones need them. So why do we have this thing, using namespace std? Comment that out and see what it shows you as being an error. All of a sudden, cout no longer works. You can fix that by coming over here and typing in std : When you have using namespace here, what it does is it tells the compiler that we don't need to prefix. the things that are in this IOStream module with STD : Kind of like if you're going to the Thompson family reunion, you can assume that everybody there is named Thompson. Is that true? No, but just bear with me. So, you know, everybody named Thompson, but if you do using namespace Thompson, then you wouldn't have to, you know, tell everybody that the last name was Thompson. By using namespace STD, we are avoiding needing this additional typing. That is considered uncouth and wrong, but it is so useful in these classes that I go ahead and do it that way. All it requires is a little bit of additional typing, though, if you want to take that out. And if you do take them out in the programs that you turn in from home, you know, I'll respect you. I did not mean to hit that. So the parts of a C++ program. We have comments up at the top. We have preprocessor directives. And preprocessor directives can be a lot more complicated than just #include. What that #include is doing is it's telling it to go out, grab that header file, and insert it into the body of this file during the compilation process. Doesn't actually change the text, you know, but during compilation, it treats it as though we're in there. There are a lot of other preprocessor commands you can put in there as well, and I don't think the book talks about them for a while. Are we in the wrong?
Sorry, we thought you were in the...
I am so sorry. I kept looking in there and I didn't see anybody, so some people have come in here.
Sorry about that.
No, it is my fault because I said we were going to switch over to the other classroom and then I didn't. Let's just assume we're going to be in here from now on. I am so sorry. All right. Here's where we are. Create a new project and just put that code in it. And if you remember how to create a project or you don't, File, New, Project, choose C++ empty, and I know I'm going way too fast because you're not even logged in yet. Choose C++ empty project, and once you get it open, do File, go to Source Files in the Solution Explorer, and click File, Add New Item. Okay, so I'm going to be blathering a bit more rather than typing, so y'all get a chance to catch up. Alrighty, so we have our namespace directive, which you can always leave out, but then you have to give the full path to the command rather than just assume that it can find it. So if I did not have that using namespace, I would need to have done that. And then we have the beginning of our function. Every C++ program you write will have a main function. However, if you're writing something else, you may see some Microsoft-specific variants of that. Let's see if we can get one of those going. I'm going to create a new project. I don't want you to do this. Let's do a Win32 console application. Then I'll go back to it. All right, welcome to the Win32 console application. La-di-da-di-da. Dum-de-de-dum-de-dum. See, and here it's got some Microsoft specific variant, int tmain. It's also got some things over here. We could add those on if we wanted to be able to pass in command line arguments. What are command line arguments? When you run a program from the command line, like dir, you can give it options. dir, but I want everything sorted by date. Same idea. You can run this program from the command prompt and then type in additional parameters and it'll run that way. Alright, so I'm going to close that. I'm just showing you that if you look at see other code and it's got variants of main, it's because it's Microsoft loves to try to claim things by changing them, and then once you write your code, for a Microsoft specific variant, then it's going to be more difficult to change it to run somewhere else. And that's kind of their goal in that. So along with our namespace, we have our main function. You can define other functions the same way. This is the return type. Int is a return type, meaning that the function returns a number. Now again, Microsoft is kind of silly and they don't force you to return something from main. But for completeness sake, we are good programmers. We are going to return something out of main. Where does this go when it's returned? Like I said, when you call it from the command prompt, you know, when you type the name of your program.exe, if you were running it from a bat file, a CMD file, that return code could be checked by that script. And then the script can know, did it succeed? Typically people do return 0 to mean that it worked, and to return a non-zero value to show that an error occurred. And so the bat file could call it and then check the return code, and if it displayed, you know, something, if it returned something other than 0, you know, it could send a message to the administrator or something, you know, letting them know, go look at the log files. I think I've already said that. And the reason that Java doesn't support return codes out of main is because Java is not being launched by the or your app is not being launched by the operating system or command prompt, but is being launched within a Java executable that you don't have control over scripting in that fashion. All right, were y'all able to? My mistake. So every block of code is denoted with the curly braces. This is how we generate our output. There are probably variant ways of doing it. I'm going to try the good old C version of it and see if that still works. Yeah, so if you wanted to avoid the use of these C++ strange looking things that you're not going to see in other languages, there are functions that you can call that will send output to the screen as well. I don't think we're going to be doing that. I can't think of a strong reason unless I just want to have a, oh, today we're going to talk about C programming and, you know, show you the differences between a C++ and a C program. And so this is called a stream. We have an output stream, an O stream, and you send stuff to an O stream using the arrows pointing in that direction. You can have other streams besides the one that go to the screen. You can save to a file with streams. I assume, because this is true in Java, that you could also write to, you know, an internet socket using the stream insertion operator. So you could open a channel to another computer and start sending things that way. Why would you want to do it that way? Because you could write your code so that it displayed stuff to the screen, and then with very minimal changes you can modify that code to save to a file. Now they show in their examples using ENDL, well actually they didn't even put an ENDL. Rather than \n. My general rule of thumb is if I already have an open quote going, I just type in /n because it's faster. But otherwise, arrow ENDL is the way to go. But that is another thing that's part of the standard namespace. So if I had this commented out, I would have to do std : there as well. And I can anyways, it doesn't break it, but it's just more typing. The interest in increasing typing and decreasing the number of typos is really the only reason why I tack that line on, even when it's considered poor taste. Why is it considered poor taste? Because it brings in a whole bunch of stuff along with just these IO commands. There are many other things defined in the standard namespace. And so you may be trying, or other programmers may be trying to define their own things that have names that conflict with things that are already declared in the STD namespace. All right. right, so hello there, that's our output statement, and then return a 0 back to the operating system. So our special characters, we've seen many of them. Begin a comment, // begin a preprocessor directive. I am going to show you another preprocessor command. You can create macros. Do this, add this command up here. # define Fred cout, and don't put a semicolon after it. And then come down here and change that cout to the word Fred. We're going to undo these changes because these are moronic, but I want you to get the idea of macros. Let's add another macro, # define done, to mean return 0. And then go down and make the last line of code done. Now see, it almost looks like we're kind of defining our own programming language there. We're not really, but what happens when this is compiled, every occurrence of the word Fred, it's like it did a search and replace, right? And every occurrence of the word Fred is replaced with cout. And then the other search and replace is done, and every occurrence of the macro done is replaced with the text return 0. So that's what the preprocessor is doing, is it's hitting every line with a hashtag in front of it, removing them, and then making the changes to the text file before it gets sent to the compiler that needs to be done, that is specified. All right, that is so silly that I am going to remove those. If I'd come up with a better version, that's great. I'll show you one that's actually kind of useful. Quite often, define pi 3.14159, right? If we're going to be doing the values, circles and spheres and stuff like that. This is still kind of cheesy because pi is defined in, a library, I believe in CMath. And in Microsoft, variant oddball, I believe it's already defined even without including any libraries. Let's see if that's true. I'm going to comment this out and then just do cout *pi EDL. No, it's not. What do you know? Okay, let's go find it. What library? Microsoft C++ pi. # include angle brace CMath. Did that fix pi? How about m_pi? All right. In the interest of time, I'm not going to waste any more time on that. I'm just going to tell you that if you wanted to do # define pi and give it a value like that so that you could use it in your programming and make it look nice, you can do that. All right, so opening and closing braces, if you just have one, it's just for the file name and # include, or it means less than or greater than. If you have two of them, it's the stream insertion operators, right? We know what parentheses are for. They group data to be sent to function calls, and they also order things inside of mathematical statements. 1 plus parentheses 2 times 3, that kind of thing. Curly braces define a block of code. We know what quotes are, and we know that semicolons end every statement that is not a preprocessor directive and doesn't precede a curly brace. So notice, everything that is a # does not have a semicolon, but everything else except for the statements that precede an open brace does, right? That has one, that has one, that has one, that has one, but this line did not because it precedes an open curly brace. So the cout object, we're using it, displays output on the computer screen. You use the stream insertion operator to send data to it. Cout arrow arrow programming is fun. You can send more than one item to the screen. Hello there. Or you can stack them like that. So I'm going to add some stuff underneath hi. Call space end quote cout on the next line me end space or space end quote semicolon and then cout arrow arrow quote maybe backslash n. Or let's leave out the backslash n, and then on the next line we're going to send an ENDL out. Cout arrow arrow ENDL. What you're going to notice is that unlike Python, it doesn't skip to the end of the line after every output statement. And there is no version of cout, unlike Java, that automatically does go to the next line. You remember in Java you had your two variants, one that did go to the end of the line and one that did not. Well, cout just flat out doesn't go to the next line. Come on. Come on. All right. Now C++ ignores white space, meaning, and that includes character turns. So I could write a program. Don't do this because this is stupid. There. How about that? That's a pretty neat program. It works. It would compile. Obviously that doesn't work in Python, but it works in C++, which ignores white space. Java is the same way. I'm going to undo all those changes. Where you'll see me take advantage of that is if I have a long cout statement, just because I'm limited in my screen real estate because I'm running it, 1024 by 768. So, if I'm doing cout and I'm putting a whole bunch of things in, by the time I get to here and I need more space, I'm going to be going past the end of the line. I don't want to scroll, so I'll just hit enter and then go to the next line and continue to type arrow arrow. I could put a colon there and then, do what I was doing here, right? Continuing every cout as its own discrete item. I'll probably flip-flop between the two. There's nothing wrong with making a really long cout statement that you do have to scroll to see. But since I'm always trying to keep all the code on the screen at the same time, I tend not to do that. I'm going to delete that line. So the EDL Manipulator, I like that name. You can use the EDL Manipulator to start a new line of output. You can even mix it up. You could do something like this. Cout, hello, space, end quote, arrow arrow, ENDL, arrow arrow, goodbye, end quote, arrow arrow, ENDL. Like that. And as we would expect, hello prints on one line, and then that sends it to the beginning of the next line, and then goodbye sends it to the other. You can use escape sequences to perform the same thing. \n does the same thing. There are other escape sequences. An escape sequence is something that is preceded by the \. There are several of them. Here's \t, which does a tab. There's \r, which goes to the beginning of the line. Let's see if that one works in C++. I know it works in C. So I'm going to do this. C Darth, and then \r to send it back to the beginning of the same line, Bob. \n. Curious about what kind of output that's going to give me. Can you tell what it did? Yeah, Bob's. Why did it do that? It printed Darth, it went back to the beginning of the line, put in BOB there, and then it went to the next line without having written over the TH. How many times are you going to use that? I have no idea. I don't take advantage of that. But for example, if you wanted to draw a little spinning symbol right while the user was waiting for something to be done, yeah, you could probably do that, right? You print a slash, and then you print an asterisk, and then you print a backslash, and then you print a horizontal line, right? You know, you keep backing up each time to get that to work. There is also one that means just go back one key space rather than back to the beginning of the line, and I don't remember what that is. So let's demonstrate the tab one. Cout Darth \T mul \n. So it should put a space, more than one space probably, between Darth and mul. I forgot my semicolon at the end. And I need to do walkabout and make sure that everybody's got all this going. Yep, Darth, and then it tabbed it over to mul. That's nice because if I had another one here, you know, it's tabbing every 8 characters. The only problem with using tab to line things up is that if you have data that extends more than 8 characters, then it jumps a whole nother tab. And we're not going to worry about that right now. Good place to walk, make sure that we're all good. So you do not put quotations around EDL. If you did, you'd see the word EDL on the screen. And that is a lowercase l, but obviously you've all already figured that out. It's not a 1. The /n escape sequence. We put it inside the string and it goes to the beginning of the next line. /n is just equivalent to the ASCII value of 10. /t is equal to another ASCII value. What is ASCII? If you talked about it in 1113, yeah, all of the basic typewriter keyboard characters have values that are generated when a key is pressed. If you press an A, a byte with a value of 65 is sent to down the wire. If you hit a capital B, a value of 66. If you hit a capital C, a value of 67. Down here, there are control keys, control codes, back from the dusty, you know, mists of time. Hey, I wonder if bell works. I wonder if we could send a ASCII value of 7 to the screen and have it ring a bell, a beep. But anyways, here's the backspace one. Tab, horizontal tab. So our /t is converted to the ASCII value 9 for display. And then so when it is printed, it goes over to the next line. If you think of this stuff back in terms of printers, like in the old days, line printers and stuff like that, it kind of makes sense. That's why there's a vertical tab ASCII value. I have no idea what that would even do on a screen. But then there's also one that does a new line, goes back to the beginning. Play with that just a little bit. We're going to define some characters. Do this. CHAR space C1, C2, C3, C4, C5. And then underneath that, C1 is equal to, and then now use single quotes, apostrophes, not double quotes. Capital D. I'm just going to spell out Darth with these letters. C2 is equal to single quote A. End quote, semicolon. And to finish that out with R, T, and H. C3 is an R. C4 is a T. C5 is an H. Now we're going to print that stuff out. So cout, arrow, arrow, C1, arrow, arrow, C2, all the way out to C5. Arrow, arrow, C3, C4, C5, and then send an EDL. And now we're going to print out the numeric value of each character. And it's going to look kind of messed up because, well, let's see what we can get going. Cout, arrow, arrow, and we're going to type in int parentheses C1, just like we did in Python. And then arrow, arrow, space, semicolon. But then copy that and paste it 4 more times and replace C1 with C2, C3, C4, and C5. So I copied it just with shift down, shift down arrow, control C for copy, control V for paste. I'm going to paste it 4 more times so that I can print out C2, C3, C4, and C5. And I want it to go to the next line, so I'm going to print out on the last little bit cout EDL. Did restart you, didn't I? Yep. All right, so it prints out Darth, and then it prints out the ASCII equivalent. ASCII stands for American Standard Character Set for Information Interchange, something like that. Okay, so 68 is a capital D, 97 is a lowercase a, 1114 is a lowercase r. The first version of ASCII didn't even have any lowercase letters. They had to extend ASCII in order to get that to happen. What does extend mean? They had to increase the character set by a bit. 6-bit ASCII only let you go up to uppercase letters. 7-bit ASCII lets you include lowercase letters. Why would adding an extra bit give you all the space for all the lowercase letters? Well, we're going to do a lecture on binary numbers, and if you've already had the lecture, then yeah, it's going to be very familiar, and if you haven't, then you'll get some new information out of it. Okay. All right, I'll be right there. Change like that H to a \n and find out the character value of \n. Would it have worked if we replaced these with single quotes? This is just my experiment. You don't have to do it. I would expect it would. Why? Because this is just the equivalent of a character, and we've already sent characters to cout just fine. So that'll work. Not even sure why I was concerned it wouldn't. Yeah. All right.
So what is the difference in the language between the double quotes and the single?
Double quote is when you have more than one letter. That's called a string.
Okay.
Right. So you use double quotes for all of these because we have more than one letter in a row. These are string constants, but if you wanted to create a string variable, like string name is equal to Joe, you would use double quotes around it. The char data type can only hold one letter, and that's when you use the single quotes, is to hold one letter. May as well add commas to that effect. Double quotes for strings of characters. Single quotes for single characters. Very good question. And in Python, it didn't matter. You can mix them up. But if you go on to take Java, the same applies. So the include directive, I've already mentioned it a couple of times. What does it do? It's a preprocessor directive. It's not part of the C++ language, and that's why we don't end it with semicolons. It's not even part of C or C++. It's just something that was added, bolted on to increase the capabilities of the compiler. And it's kind of too sad that Java doesn't support compilers as well. I mean, preprocessor directives. What it does is it actually goes and grabs the contents of another file and puts it in the program. Here's maybe something of interest. Go up here, highlight one of these terms like cout or EDL. Right-click on it and do go to definition. See what I did? I highlighted that word. I right-click to go to definition. It'll take me down into the bowels of that header file, and we'll see some definition for what EDL means. And it's a lot more complicated than we ever would have dreamed. These are using templates and they're using classes, stuff that we certainly don't know about yet. I'm going to close that window now. But you can do that for anything, right? Down here when I'm printing out C5, if I wanted to know where C5 is declared and it wasn't so close, right? I would highlight C5, I'd right click on it, I'd go to definition, and it would show me that it was declared there. Variables and literals. Well, we've already got a whole bunch of literals in our code. All the literals are these things between quotes. Why are they called literals? They're literally typed into the program. These are also called unnamed constants. It is something that if in order to change the value of it, you actually have to edit the source code, right? There's no way to come in and have the user change the value of Joe while the program is running. You have to go and change the source code to it. So it's an unnamed constant. A variable is something that has a name, but it points to a location in memory, and that memory can be changed. So we can put stuff in it. Here we put Joe into it, but later on we could put Bob into the same variable if we so chose. So underneath that name is equal to quote Bob. So every variable has a couple of things that are associated with it. It's got a type, it's got an identifier, also known as a name, and it's got a value. So down here, what is the type of that variable?
Char.
Yeah, char. What is the value of it? Well, it doesn't even have a value yet until we get to here. So it's an uninitialized variable until we get to this point. And its name, its identifier, of course, is C1. Looks like I'm not even creating a separate notepad file like I usually do. So just tack some stuff on here. I'm going to create a multi-line comment by using /*. That way I don't have to preface every line with //. Okay, variable is a named location in memory that has an identifier, parentheses name, a type, like such as int, string, float, double, char, and then a value. Although it may not be initialized yet, right? So, but I'm going to take that out. So if you left off the parenthetical things, it's still a correct thing. If I asked you for the three attributes of a variable, I'd like you to cough up identifier, type, and value. And that's true of any language, not this language. Even in Python, where you don't declare your variable specifically with a type, they still have a type. It's just that Python lets you override it with another type, you know, willy-nilly. You can say x is equal to 3, and you can turn around and say x is equal to quote Bob, and it doesn't care, but that doesn't work in this language. Now that we have declared name to be a string, if we turn around and the name is equal to 3.14159, that's not a compatible type. And I just proved this in my C class, that for some reason it is really generous about our types and not counting that as an error, which is absurd. I can't explain why. I'm going to not worry about it. Let's just kind of take it on faith that once you declare a variable as a specific type, you should not put anything else of any other data type in it, and usually the compiler is going to catch it and complain about it. But C++ is not as picky about that as Java. That absolutely would have been an error in Java, a compilation error. It would not have run. It would not have compiled in the first place so that it could run. So a variable has a name and a data type. They list two of the things that I like us to remember, and it also has a value. Must be defined before it can be used. Python let us do this. Name is equal to, Bob. Great. We could do that. In this language, you have to define it first before you can do that. That's why we give it a type. In Java, you had to use uppercase S. In this one, you have to use lowercase s. You just remember that. How many of y'all have had Java? I'm going to stop saying, in Java, you blah, blah, blah. How many have had Java? Is that a yes for you?
Yeah.
Oh, well, you're in it right now. Okay, so I better keep pointing out those little differences, and the rest of y'all are going to get tired of me saying that. So what is a literal? It's a value that is written into the program's code and not typed in by the user or read from a disk drive. Hello there, that's a string literal. 12, that's an integer literal. 12.5 or 12.0 would be a floating point literal. Not a flat literal. Float. So in this code it says int apples, apples equals 20. That's a integer literal, also known as an unnamed constant, but the value of that unnamed constant is stored in this variable apples, which means it's not a constant anymore because apples contains that value. It's like you photocopied the constant and you gave it to that variable apples, and it can change it if it wants to. It's just got a copy of the data. And these are string literals. Today we sold and bushels of apples. So identifiers are variable names, function names, class names. An identifier is a program-defined name for some part of the program. Variables and functions. Right now we only have one function, but that is an identifier. We have lots of variables, or at least a few. Name is an identifier. C1, C2, C3, C4, and C5 are all identifiers because they're variables. We don't have any others yet. Identifiers follow specific rules. An identifier, parentheses name, same rules as in Python, same rules as in Java. Cannot start with a number. Can be numbers and characters. Some languages allow $signs, some do not. But cannot be special symbols except underscore. Let's just take that as a definition, and some languages do allow $signs. I believe C++ is one of them and Java is not. So if I went down here and I tried to create a variable, int x $sign is equal to 32, the Microsoft compiler doesn't treat that as an error. It goes ahead and lets you use that. A lot of other languages would not. So those are our general rules. That, it can be characters and numbers and underscores. Why don't we just list them all? Cannot be special symbols except the underscore. I'm going to move cannot be and cannot start with a number underneath that, so that we say what it is before we start saying what it isn't. All right, C++ keywords. This is a much larger list than the C keywords. If you were taking a course just in pure C, the list of keywords is quite a bit smaller. We're probably not going to learn what half of these mean. Some of them just flat out don't work, I don't think. I don't think goto is a legal keyword. I think it is just a reserved one to prevent you from actually trying to use it. But we've seen some of these before in other languages. We know what a return does. I'm not seeing a lot of others that you would know just straight from Python. Some of these things are, an if, there we go. While, that's another keyword. And the primitive data types like int, double, and long, and char, are all keywords as well. These are reserved words, meaning that you can't use them as variable names, right? So I can't use the word switch or case as a variable name. If I come in here and say, I wanted to do this, string case, don't type this because it's going to be an error, is equal to case of the missing shrew, whatever, right? Like that. That's an error because this is a reserved word. We can't use it for our own purposes as an identifier. So variable names should represent the purpose of the variable. You want to pick good variable names. A good variable name is one that is clear in meaning. Now, in this class, I tend towards very short variable names. Why? Because it's easier for y'all to type. But you should pick reasonably good variable names for your own programming. So, like one word or two words. You can't put a space in it, but you can jam the two words together. Items ordered is a good variable name. I would be a bad variable name, or IO for items ordered. Because why? Somebody would look at it and they'd see that IO and they would have no idea what it meant. But items ordered is real clear as to what it means. And there are different naming conventions. Some people like underscores. That's old school. And it's like 60s and 70s. At some point, what's known as camel case kicked in, and that's called camel case. Uppercase is all caps, lowercase is all lowercase. Camel case is when it starts with lowercase and then it has some uppercases mixed in. I didn't make the term up. Silly name. So the purpose of the variable is to hold the number of the items ordered. Now variable names are just for our purpose, not for the purpose of the computer. The computer doesn't care whether we called this C1 or something else. I could have called this Bobby Dylan. And as long as I called it Bobby Dylan everywhere it occurred, the code is going to work. Right? Now that's a stupid variable name, but honestly, C1 was kind of a stupid variable name too. It didn't convey much information. On the other hand, for a simple counter, right, like in a for loop or a while loop, or if you're just holding a single character for future analysis, a short variable name is okay. You don't have to create a counter and call it the word counter, right? Everybody will know, every programmer know that if you have, for x equals 0, x is less than 10, that there's going to be a counter called x. So that's clear. Otherwise, you should pretty much avoid single letter variable names. I'm going to undo that change. I was just illustrating that the names do not matter to the compiler as long as they're used, everywhere that they should be. They're just for our purpose and understanding what we wanted our program to do. So identifier rules. The first character must be an alphabet or an underscore. Can we use weird ASCII characters as a variable name? Can I do this int and then type in alt 187 is equal to 3? I'm just curious. Yeah, some Unicode characters. Do you want to resave this file as Unicode? Neat. Okay, if I wanted to use that as a variable name, I could. Why is it allowing non-English characters as variable names? Because you may be programming in Korean, right? Or something, Russian or whatever, and you want to give a variable name in your own language. You don't want to have to use the English word name when you have your own, language and character set to specify the same thing. So it mentioned Unicode. What is Unicode? Well, the ASCII character set that I showed you is only for pretty much English typewriters, which is great for Americans and people from Britain and stuff like that, but it's not good for the French and the Germans and the Russians or whatever. And so a larger character set was created that contains all of those languages. and it's called Unicode. One code to rule them all, and in the darkness bind them. Right? So it can't just be one byte, because one byte could only hold one of 256 different values. It's a multi-byte character set because there's thousands upon thousands of characters in all the human languages. So when I changed it to something weird like that, it said that's not ASCII. Do you want to save it as Unicode? And I did. So somebody creating, Russian or Korean or whatever, they would be using a Korean keyboard, but they would be creating Unicode versions of the CPP file.
So what was the command to be able to type that in?
The way you type these in, if you're using Windows, doesn't work on Macs, is you hold the Alt key down, then type in a 3-letter code, 1, 5, 9, and then hold up on the Alt key, let up on the Alt key. And if you memorize those, you can get hearts, and you can get the franc symbol like this is, or you can get the pound sign for British pounds. Euro is probably in there. You can even do more than 3-character codes because Unicode is larger than 3 characters. So what is 1555? Neat. A double exclamation point. What is 2000? I'll come check. Yeah, but you have to use a numeric keypad if you're using.
Oh.
Sorry, I did not specify that.
There we go.
So if you're using a laptop without a numeric keypad, you're kind of hosed on that.
Yeah.
So yeah, sorry about that. So valid and invalid identifiers. This one's totally good. And if I drag this off the screen so that we can't see the answers. Is this one good? Yeah, sure is. There's nothing wrong with it. How about the one underneath it? Does it look like it violates any of our identifier rules? If you don't know, take a wild guess so we can go on.
It's good. Nope. It's good.
Yeah, no. Why? Because it's all letters and numbers or underscores. It doesn't have any illegal signs in it. Illegal signs mean punctuation. Because obviously some of these weird characters that we were typing in are not considered punctuation. So this one is valid. How about total dot sales?
No. Good.
It is not valid. It might not give an error if you have an object named total and you're referencing a member of the total object. You'll see that syntax, right? Something dot something. You've probably seen that before, but it's not a variable name. It's a variable that's attached to an object. This is a variable that's attached to an object called total. That's what the dot means. How about, I don't know why I'm walking over here when I'm just going over here. Anything wrong with that one?
Starts with a number.
Starts with a number. How about that one? This book says it's wrong because only underscores are accepted. However, the C language actually supports it. So by book, it's wrong. Other languages, other than C, maybe it's just a Microsoft quirk that dollar signs work. There are differences in Microsoft's version of C and C++ than other languages, although over time it gets to be more and more standard, which is, a good thing. Why don't we take a break? Come back here at 8:15. So if anybody needs to use the bathroom or something. Yes, sir. And we don't see anything missing a semicolon above that line. Sometimes there's a hidden invisible character, especially if we were typing in those Unicode characters. Oh, look. We have to use an equal sign. Yeah.
hope so.
I don't want it.
Hey, you're bringing a whole song.
So what is an integer? It's a whole number. And I didn't stop the recording, so there's a 6-minute delay in the video. Alrighty. Anyways, the integer data type. Whole number including 0. There are different kinds of integers. There are, let's call them 4-byte integers, meaning that the number has to fit within 4 bytes, which is equal to 32 bits in computer memory, because there's 8 bits in a byte. Then there are 8-bit integers. 8-byte integers. There are signed integers, which can be positive or negative. There are unsigned integers, which can only be positive. Why in the world would you want to create an unsigned integer that could only be positive? Python doesn't have unsigned integers. Java doesn't, as far as I know. The reason you would want unsigned is because the way I really need to do a lecture on bits and bytes. The way that a negative number is distinguished from a positive number is by using one of the bits of information. The first bit indicates whether it's a negative or a positive value. But if you can leave that out, if you don't have to have that information, you have a whole nother bit in order to hold what the value of the number is. I really do need to lecture about bits and bytes. So we're going to veer off from the slides. Should just find a good video on this and make y'all watch it. But nobody could possibly lecture about it as good as I do. Alright, so a bit. It's either a 0 or 1. Why? Because a computer switch. I mean, back physically, like in the 30s, before any kind of circuits had been invented other than relays. Your relay was either open or closed. If it was closed, current was going through. That's a 1. If it was open, then no current could be flowing through. And then with vacuum tubes, a vacuum tube is essentially just a light bulb. If it was glowing, it was a 1. If it wasn't glowing, it was a 0. So a byte, 8 bits. That's the common clustering that is now used. Until that was decided upon, some people, were using 10 bits, and someone were using 6, and someone using 14, and whatever. It's been settled upon that a byte is 8 bits. And what does that mean? You could have blah da 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 up to da 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 da. Now, do I have 9 there? Yeah. Okay. So those, and any combination, right, in between. These are all valid byte values, and so on. Now, I don't know without checking, without adding them up, which of these is which, but I do know that that is a 0. No bits is a 0, and all bits in a byte would add up to 255. Why 255? That's a magic number, isn't it? Well, let's figure it out. Let's think about decimal numbers. Base 10. If we have the number 3,294, what does that mean? It means 3 times 1,000 plus 2 times 100 plus 9 times 10 plus 4 times 1. If you add all those together, you get 3294. Congratulations, we converted base 10 to base 10. Big accomplishment. But the concept, if I took these and replaced them with the powers of 10, this is 3 times 10, and although I'm going to use this character, C does not support it, so don't think that you can take the square or the cube or something like that by using that character. Even in Python we had that, but we don't have that at all in this language. We don't have either option. If we want to raise something to the power of something other, we use the function POW, but that's besides the point. So that's 10 to the power of 3, 10 to the power of 2, 10 to the power of 1, and 10 to the power of 0. So 10 to the power of 3 is 1,000. 10 to the power of 2 is 100. 10 to the power of 1 is 10. And 10 to the power of 0. Any number to the power of 0 is equal to 1. Okay, so, as we learned them in grade school, that's the ones place, the tens place, the hundreds place, the thousands place. Why? Because this is 10 to the power of 0's place. This is 10 to the power of 1. This is 10 to the power of 2. This is 10 to the power of 3. Now what if it's in binary and we had 4 digits? And like I said, I know some of y'all have sat through this lecture because you had me in prior classes, but not everybody. Maybe your other instructor taught you, maybe not. So you have 4 bits, 4 places. But since it's binary, it's only got, that's called base 2 because there's only 2 possible values, right? A digit in our language has 10 possible values. That's why it's called base 10. Binary is just 0 or 1, so it's base 2. So if we figure out the values of these guys, this is 2 to the power of 3. This place is 2 to the power of 2. This place is 2 to the power of 1. And this place is 2 to the power of 0. And so if we were going to figure those out, that's an 8. 2 times 2 times 2 is 8. 2 times 2 is 4. 2, and then any number to the 0th power is 1. you could kind of figure it out, right? What's the next one going to be? What's the pattern? It doubles each time. 16, 32, 64, 128. So if we have an 8-bit number, 128, 64, 32, 16, 8, 4, 2, 1. Those are our 8 bits, possible values. If they were all ones, well, we'll get there. So if we have this number, 0, 0, 0, 0, in base 2, what is it equal to in base 10? Well, all zeros is 0. No mystery there. How about 0, 0, 0, 1? Well, we have 1 in the ones place. We have 1, 1. So that's 1 times 2 to the power of 0, which we could rewrite as 2 times 1. No. 1 times 2 to the power of 0, which is the same thing as 1 times 1, which is the same thing as 1. Think of this as an odometer. We're driving along. If we were driving along on our base 10, and we had like 2 or 3 places, we hit our first mile marker, we hit our second, our third mile marker, 4, keeps rolling over. Don't know if any of y'all are old enough to have ever had a car where they actually physically roll over, or owned an alarm clock where the numbers physically turned, but what happens there? It becomes 0, 10. More technically, conceptually, we just know, right? Instinctively, because we've lived with this so long. But what's happening? We have maxed out. This is the largest digit that exists in base 10. And once you add 1, what do we have to do? We have to reset this one back to a smaller value, and then we increment the next placeholder by 1. Right? Carry it over. And so now we can keep cruising along in our imaginary car again. Now when we're going to add 1 to it again, we have maxed out the ones place. So we're going to reset it back to 0, and we add 1 to the tens place. And if we kept going, you know what happens when we get to 0999. Can we add anything more to 9? No, we cannot, so we zeroed out again, and we add 1 to the next place. Okay, but can we go any higher than 9 there? No, we cannot, so we zero that out, and we add 1 to the next place. All right, cool. All right, obviously we already knew, but I wanted to explain it in a little bit more detail because now we're going to hop in our car that counts in binary. 0, 0, 0, 0, 0, 1. What's next? We have already maxed it out. You can't have a number larger than 1. So we're going to turn that back to 0, and we're going to carry over to the next. So it becomes 0, 1, 0. Now, we drive another mile. Yeah, we can certainly add 1. We can increment that. Now what happens? Okay, well, when we want to add 1 to that, we have maxed it out. A binary can only go 0, 1. There's no such thing as a 2, so we have to reset that back to 0, and we're going to carry that over and increment that one. But that one is maxed out, right? It goes like that. Now I'm just going to fill in the rest of them real quickly. Okay, so there were 8 different possible values. Why do I say that? Because just looking at it, 1, 2, 3, 4, 5, 6, 7, 8. What if it was just 2 bits? 0, 0, 0, 1, 1, 0, 1, 1. 4 possible values. What if it was 1 bit? 0 and 1. So that's a 1-bit series. This is a 2-bit series. This is a 3-bit series. I'm not going to do 4 bits because I don't feel like typing that much. But how do you figure this out? 2 to the power of the number of digits. So if you have 1 bit, it's 2 to the power of 1, gives you a total of 2 different. If you have 2 bits, 2 to the power of 2 is 4 possibilities. If you have 3 bits, 2 to the power of 3, 2 times 2 times 2 is 8. So 4 bits, 2 to the power 4. Well, it's just going to be double, right? So 16 different possibilities. 5 would be double that. 6 would be double that. 7 would be double that. I've messed something up. I guess it is. Yeah, that is correct. And 8 is 256. Different possibilities. So, remember your Nintendo was an 8-bit computer, so the colors that it could display on the screen was from a palette of one of 256 values. So the graphics weren't real cool. And then you had your Sega Genesis or your Super Nintendo, and 2 to the power of 16 is 35536. So that's why you had a much broader color palette, so you could paint prettier pictures with a 16-bit video card, 16-bit Genesis or Super Nintendo. And obviously computers now come with great color cards that can support billions of colors. So where was I on this? We have the number 0000. I need to go and copy this thing back up here, which had the place values for them. 1, 2, 4, 8, 16, 32, and 64. But really at this point I just care about 1, 2, 4, and 8, right? Because the farthest place is a 1, and then we have a 2's place, and then we have a 4's place, and an 8's place. So the number 0000 just adds up to 0. 0001 is equal to 1 times 1. 0010 is 1 times what? 2. 0011 is 1 times 2 plus 1 times 1. 0111 is what? It's 1 times what? Almost. Yeah, 4 plus 1 times 2 plus 1 times 1. Now it's tedious typing all this 1 times, right? So if I asked you to show me why 111 was equal to what it is, which is 7, you could just say 4 plus 2 plus 1. And that means that this one is 2 plus 1 is 3. That one is 2. That one is 1. So all ones, 1, 1, 1, 1, is 1 times is 8, like you said, plus 4 plus 2 plus 1, which gives you 15. But you said that 4 bits could hold 16 different possible values. Yeah, but 0 is also a possible value. So the values from 0 all the way out to 15 is a total of 16, right? Why in the world did I want to talk about that at this point in the slides? Let me go back and see. Integers, because I wanted to talk about negative and positive integers. How would we indicate that we wanted a negative number? This system only works for positive counting. Well, if we wanted some way to indicate that a number was negative, we could just make a contract with ourselves that if the first bit was set to 1, it meant it was a negative number. And if it's set to 0, it's a positive number. So in effect, 1111 would no longer equal 15. It would be a negative number. The exact mechanism that it uses is not as simple as we might hope. If we have like 1000, what would we expect that to be? We'd expect that to be 4, right? And then if we prefixed it with a 1 to make it a negative number, it wouldn't just be negative 4. It's not quite that easy. It does something called 2's complement, which we might talk about later. But specifically, that eliminates the ability for us to use this as a valid value, right? It knocks it out of the running, and we can only use 3 bits for counting. And what did we say 3 bits can hold? Up to 8 different possible values. So if we need the ability to count both positive and negative, we can only count 8 possible values. So assigned 4-bit value only has 3 for the content and then 1 to control whether it was positive or negative. But if it's an unsigned value, then you get all 4 bits, and you can hold 16 possible values. So it can hold a value that is, twice as large, in effect, as assigned. So if you use unsigned, it's the same number of possibilities, 16 possibilities, but they go higher, right, 0 to 15. Whereas if it's assigned, you've lost that first one, and you can have values like from negative 15 up to positive 15. Slightly different than that, but close enough for our purposes, just to understand the idea of signed and unsigned bits. Alrighty, so I want y'all to play along. Go ahead and open Notepad or something like that. And if we write these places out, I'm not going to do that. 128, 64, 32, 16, 8, 4, 2, and 1. I'm going to follow the convention of putting a space every 4 bits, just so it's easy to understand. I want you to convert these binary numbers to decimal numbers. And how do I want to, and we'll do like the first 2 together. Okay, so what is this? That's the 2's place, and that's the 4's place. So that is equal to 4 plus 2 is equal to a 6 of total. What about this one? What place is lit up? 1, 2, 4, it's that place, right? So it's equal to 16. And the rest of it is all 0, so we don't need to add on anything. Go ahead and do the next 4. I suppose I could space them out to make them easier to see, but hopefully you can just count them over. So somebody tell me the values of those 3 bits. What are those? What are the places of those 3 bits?
8, 4, 2.
Correct. So that's an 8 plus a 4 plus a 2, which added up, I guess, is 14. How about that one? What is that place? It's the 3rd bit over, so that's a 32. And then what is that one? That's 1, right? So that adds up to 24. All right, now we only have 2 bits lit up. What are those values of those 2 bits?
1, 2.
Yeah, that's a 4 and a 2. Now only hear one person answering. I hope the rest of y'all got these. And how about that one? What do those add up to be? Yeah, that's 15. And why is that? Somebody tell me the place values involved in those.
8, 4, 2, and 1.
Yeah, 8, 4, 2, and 1. So that's 15.
Isn't that supposed to be 33? Is that 24?
Okay, I'm sorry.
The 4th one down? Yeah.
Where did I get 23 from? What in the heck was I typing there? Was that supposed to be 32?
33 total.
Yeah, so it's 32. Yeah. Thanks, guys. That was pretty. All right, there we go. Thank you for catching that. All right, we could also talk about hexadecimal at this time, but I think that's enough. I do want to show you how to convert back from a decimal number to binary, but I don't think I'm going to ask it on an exam. But I do want y'all to have the confidence. How do you do it? Well, I type it. I pull up the Windows calculator. I set it for binary, and I You didn't tell me the answer. Yeah, that's one way. All right, if it's a positive number, like I said, negative numbers use 2's complement, which I don't feel like we're doing right now. I guess that's not going to go any higher. Oh, right. What you do is you take your number. Let's use one of the ones that we did previously. What was one of the numbers on our list? 33. Guess we don't have a better pen. You keep dividing by 2, and the remainder is what you do. So 33 divided by 2 is 16. And what was the remainder produced by that? Had a remainder of 1. 16 divided by 2 is, was it really 30? I'm going wrong here. Okay, I'm going to run with it. So 16 with a remainder of 0. 16 divided by 2 gives us 8 with a remainder of 0. 8 divided by 2 gives us 4. Why not write 1 there? With a remainder of 0. 4 divided by 2 is 2 with a remainder of 0. 2 divided by 2 is 1 with a remainder of 0. 1 divided by 2, you can't get any lower, so it's 0 with a remainder of 1. And then you write them from bottom up. So this is equal, and in this case it wouldn't have mattered, right? But that's equal to 1, 0, 0, 1, 0, 0, 0, 0, 0, 1, 1, 0, 0, 0, 0, 1. And I think that's what we had, except we had it in 8 bits. Does that look right? Is that what our quiz question was? Okay, yeah. All right. I'm just going to pick an arbitrary another number. How about 61? So 61 divided by 2 is 30 with a remainder of 1. What's 30 divided by 2? 15, no remainder. 15 divided by 2 is 7 with a remainder of 1. 7 divided by 2 is 3 with a remainder of 1. 3 divided by 2 is 1 with a remainder of 1. And 1 divided by 2 is 0 with a remainder of 1. And then you count from the bottom up, so it's 1, 1, 1, 1, 1, 1, 1, 1, 0, 1. And if you wanted to pad it out with enough bits to fill it to 8, 1, 2, 3, 4, 5, 6, 7, 8, like that. That's the easiest way. Are there other ways? Yeah, what I used to do before I learned this method is I would go, okay, I need to be 61, and I have 8 bits to play with, right? 128, 64, 32, 16, 8, 4, 2, 1. And so I'd go, okay, are there any 128s in 61? No, because that's too large. Are there any 64s in 61? No, because that's too large. Are there any 32s in it? Yeah, there sure are. And so 61 minus that 32, I think we'll 29 or something like that. And are there any 16s in 29? Yeah, there are. So 16, 29 minus 16 is 13. Are there any 8s in it? Yeah, there are. So 13 minus 8 is 5. Are there any 4s in 5? Yeah, there is. I guess something's nagging me about this. Are there any 4s in 5? Anyways, you get the idea. You know, it's a harder process. Essentially, fundamentally, underneath it all, it's the same thing. But so you can convert from decimal back to binary in that fashion. But I'm not going to ask you to do it. I'm not going to make you quiz. And for those who were listening to the recording, I hope that was educational for you. Okay. Let's keep going on. I talked about the difference between unsigned and signed. An unsigned int can go twice as high as a signed. A short int is 2 bytes long. All the numbers I showed you are 1 byte. But, so they only had 8 bits to play with. So the maximum value they could get up to, if we added up all of them, was 255. But with 2 bytes to play with, you got 16 bits. And so we could keep doubling that number, and we would figure out that the maximum number is 65535. So the maximum value of an unsigned short bit is 65535. 0 to 65535. Because it's unsigned, it means it can't go negative. But that means that the maximum value of a signed 2-byte int can only go half as high, right? But it also has the negative range as well. Same number of possibilities, it's just that, one goes taller because of that signed bit not being used. So in this language and in Java and in a great many others, not Python, an int is 4 bytes rather than 2. So it can hold a much larger number. Remember that formula we were using to calculate how many different values there were? It was 2 to the power of n. So 2 to the power of 16, which is a short. Okay, so let's say that. A short int has 16 bits. So an unsigned short int, 2 to the power of 16, is 65536. Do I expect you to memorize these numbers? No. But if you had a calculator and I asked you to calculate the number of values that 7 bits could hold, you could do it. It'd be 2 to the power of 7. Okay. And then a regular int, an unsigned int. Since a int that's not short has 32 bits, because it's 4 bytes long, is 2 to the power of 32, which is a vastly larger number. I certainly don't have it memorized. 2 to the power of 32. Yeah, 4 billion equals a number greater than 4 billion. That's for unsigned. If it's signed, it can only go half as high, but it can also go negative. So a signed one would be, from negative 2 billion up to positive 2 billion. Then there are other types. There's one called long, a long int. This is where Microsoft is insane, because a long ought to be 8 bytes, right? Because if an int is 4, a bigger int should be 8. But Microsoft, and I'm not sure if every other compiler out there follows the same paradigm, has decided that a long int is also just the same thing as an int. That's not true in Java. So the Java programmer back there, remember that a long has twice as many bits as an int. So we're not going to talk about longs, but we are going to talk about longs. Isn't it an absurd thing to say? What kind of data type are you using? Oh, I'm using longs. It sounds silly, but it is 8 bytes long. So an unsigned one. How many bits are in 8 bytes? If a byte is 4, then 8 of them is 32. And 2 to the power of 32 is humongous. That's a technical term. Let's figure it out. 2 to the power of 32. Something's looking odd about that.
8 to the
It's 64, isn't it? Derp herp. Alrighty. Okay. I knew that was not right. So thank you for correcting me on that. 2 to the power of 64. Much larger value. Yeah. A 1 followed by 19 zeros. So, an int is a great value, is a great way. If you're using a signed int, it can only go up to half that, so 2 billion. 2 billion is a nice large number, but would it hold the United States debt? No. 8 bytes would be better for that. So that's what this chart is representing here. The largest value of a unsigned short int is 65,000, like I said. The largest value of a unsigned long, I skipped unsigned int. Unsigned int goes up to 4 billion, or 8. Yeah, 4 billion, so the signed version of it goes up to 2 billion. The largest version of an unsigned long goes up to 18 quadruple gillion, and so the signed version and all of it goes half as high, but it also goes negative. Do you have to memorize these numbers exactly? No. What I want you to remember is that a short is for numbers less than 32,000. A long is for, an int is for numbers less than 2 billion. Larger than that, use a long. And the unsigned version of it gives you, twice that. So an unsigned short can get you up to 64,000, but you wouldn't be able to have any negative numbers. So that's rule of thumb. If you wanted to figure out more exactly, you'd use that 2 to the power of n business. But you could carry that too far. Like if you're going to store somebody's age, you could say, well, nobody's ever going to be 32,000 bytes long, so I'm going to use a short int. You could, but most people don't really care. It's not like the computer's going to run faster because you only used 8 bits rather than, or 16 bits rather than 32. So you can pretty much just use int, just all the way through. If you want to. I mean, if you feel like it, you could restrict your data type to a smaller data type. Is there one shorter than short? Short is 2 bytes. Is there a 1-bit data type? Yeah, char, C-H-A-R, which you use to hold ASCII values, but you could also use it as a number, and it would give you 1 byte. So as long as your number is 255 or less, you could store it in a char data type. They don't list that on this page, though, because it's not really considered an integer type, but it is an integer type. It's just an integer type that is treated as though it's an ASCII character. So you can define variables in different ways. You can do them on separate lines. Int length, int width, unsigned int area. You can do so on the same line. Int length, int length comma width, but we couldn't put area on the same line. Why? Because it's a different type. Right? It'd be just like if you had, int x comma y, but then you had string z. Could you really make it int x comma y comma z? No, because z is a different data type. Do I like personally declaring multiple variables on the same line? Probably not, unless they all have a very similar meaning. Like when I did char C1, C2, C3, C4, and C5. They all had a similar meaning, so I didn't mind declaring them all in the same line. On the other hand, since I'm trying to save real estate, I might define all of my ints on one line. Your choice. Variables of different types have to be in different definitions. Now, I said that C ignores white space. C++, I think I did. It's confusing teaching C right before the C++ class comes in because I have a hard time remembering what I just told them. Okay, so anyways, since it ignores white space, you could do that, but that's really considered poor taste. I wouldn't do that. I did mention that, right? How it ignores white space and you could make an entire program that was one line. Okay. Alright, so an integer literal is a number that's hard-coded into it. How do we know it's an integer literal? Because it doesn't have a decimal point. If you need a decimal point, you're not going to be able to use an int. You're going to use a different type. You're going to use a floating point number. And just like there were different kinds of ints, there are different kinds of floating point. But there's no such thing as an unsigned floating point. So at least that's a little bit easier. So here they had 3 integer literals thrown in, also called unnamed constants in other books. -20 was an integer literal, 4,000 is an integer literal, and so is 18,000. So integer literals are stored in memory as ints by default, but if you need to make it a long, you can tack on some L's after it. Now that slide just showed us, okay, I'm vexed enough by that to verify that it really is a long 32-bit in Microsoft C++. Yeah, it's only 4 bytes, just like an int is. Microsoft gives you, or maybe it's a C++ specification, you can specify exactly how many bits you want to use if you prefix it with underscore. I want to see if that's true for us. If I go down here and I type in underscore int 8 and create a variable called x, underscore int 16, call it y. That's kind of that appeals to me, right? Rather than memorizing what a long is versus a short versus a whatever. But anyways, that's the same thing as a character. That's the same thing as a short int. This is the same thing as a normal int or a long int, and this is the same thing as a long. Now when you're using short ints or long ints, you can leave off the word int. You can just call it a short, and you can just call it a long. Do I recommend you do it that way? It's up to you. So anyways, if you have a number that is too big, like if we did this, I have a long, and it's called the national debt, and I don't know what the national debt is, but it's in the trillions. So let's say it was like 32, and then trillion is 12 sets of zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's going to be a syntax error. At least it better be. Yeah, fine. The C++ compiler is so...
Long is 10 to the 19th, right?
Right. And so the maximum value of 10 to the 19th is far larger than that. This fits in a long, but this is not an integer. It's way too big to be an integer. So I want to kind of prove that that's not right, even though it's not showing it as a compilation error. The Java compiler is much stricter about type errors. Like if I define an int, and I say it's age, and I try to put that number in there, and then I print out age, come on, fingers work, is equal to age, NDL, it's not going to print that number. Instead, it came out with negative 1.8 billion. Now, I surely wish that it had actually. As a matter of fact, let's just do this. Print out that number, 32 trillion, 32, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. NDL. Is it going to print out 32 trillion? And the answer is no, it's not going to. Oh, fine. Alrighty. If you wanted to specify that this was a long, you would suffix it with LL. In Java, you just use a single L because you don't have a long data type. You have a long, which is an 8-byte data type. But anyways, that would specify that it was an 8-byte rather than a 4-byte. If you prefix a 0 in it, it's base 8. Does anybody use base 8? No. But, so I'm going to ignore that. But if it starts with 0x, it's called a hexadecimal number. It's base 16, which we haven't talked about yet, but we'll come back to that concept. All right, the char data type, the char data type, holds characters or a very small integer value. Why? Because it's 1 byte. So the largest integer it could hold would be 255. And it's from the ASCII character set. So they have to be enclosed in single quotes to indicate that they are characters rather than strings. So a character string is just a sequence of characters followed by a null terminator at the end. So when we type in quote hello end quote into the editor, what is really being stored is a byte that's equal to an H followed by another byte that's equal to an L, by another L, by another L, and by an O. So when we had DAR, D-A-R-T-H there, we saw the byte values, the byte equivalents. That's really what is in memory behind the screen. So the string class, it's a special data type that supports working with strings. C++ originally shipped without a string class, and it has a data type called string, but it's not very useful. It's just a raw, character array like we were seeing here. But we like the abilities that the string class gives us, like the ability to add two words together to concatenate them, or to count the length of the string, with a function call. So they did create a data type called string, but to bring it in, you have to use # include string. And then once you have that, it's actually a class. You can create variables of that type, string first name, comma last name, and then you can associate values with it. The first name is equal to George, the last name is equal to Washington. And then you can see out them just like you can the numbers. So, string movie title. Movie title is equal to Wheels of Fury. My favorite movie is movie title. And so when it ran, it would say my favorite movie is Wheels of Fury. Now, honestly, I don't even know if that is a real movie. Sounds good, though. Alrighty. So floating point data types are when you have a decimal point. So the number 32 is an int. How about 32.0? It's a whole number, isn't it? No, it's really not a whole number. It's got that decimal point in it. Even though it looks like an int, it's stored in memory completely differently. If you looked at the individual bits of a floating point number, even if it was 32.0, it would be dramatically different than the integer representation. Why? Because ints are stored as two things. And I hope my brain helps this. It's got an exponent part. You remember scientific notation where you have 1.23 times 10 to the power of 8, something like that? That's called something, and all my brain is throwing at me is meniscus, which is a chemical term for something completely different. Oh, fine. The coefficient, the base and the exponent. Okay, so floating point numbers have to be stored as a coefficient and an exponent, right? In order to have such large numbers, right? So like if you had, like I said, 3.2 times 10 to the power of, 129, or, or 8, whatever. 16. That is way larger than can be stored in an int, but it can be stored in a float. It just has to use some of the bits to hold the coefficient, maybe half of them, maybe 8 of the bits are used for the coefficient. I don't think quite that many. And then 8 of the bits are used for the exponent. The balance of the bits are used for the exponent. So they're stored completely different. And so 3.2 is actually 32 is actually 3.2 times 10 to the power of, I think that's correct. Looks weird, right? But that is actually the case. If you typed in 32 and then you hit the exponent key on your calculator, is that right? Because 32 would be to the power of 0, so in order to move the decimal over, no, it's to the power positive 1. Man, my brain is broken today. Thank you. Okay, so like that. So when it's stored in memory, it would put 3.2 and it would put 1 in it. But they're binary values actually. So 3.2 would be a binary version of it. But it's actually stored as 32. There's no point involved in it. And then this exponent is adjusted appropriately, and that's why I was thinking of -1. Anyways, okay. So floats are stored in memory differently than ints. That's what gives them the ability to have the exponents. So they have a larger range, but they are less precise. Why? Because you can't use all 4 bytes to hold the coefficient. It only uses like 2 or 3 bytes to hold the coefficient, and then the rest are used for the exponent. But with the exponent, you can get much larger numbers, right? But they're not as precise. If you need something that's precise all the way down to the last digit, a float would not be the right way to do it. On the other hand, if you're using fractional numbers like 0.000703005 or 6, you got to use a float. There's no integer type that could hold a number like that. I hope that's kind of making sense.
So does it just truncate them, or does it round?
Right. I can't say whether it rounds or truncates. There is a difference. My guess is that it truncates. But you do get a lot of precision. A float can have up to 38, an exponent of 38. So it would be hard for us to demonstrate whether it's truncating or not. Let's see how many decimal places are in the coefficient of a float. Probably not going to tell me. Precision of float in C++. Well, we can find out. Just like they were showing. Let's divide 1 by 3 and print it out. Experimentation. C out 1 divided by 3. EDL. Except I'm going to make it 1.0 divided by 3.0 just to make sure that it does floating point division rather than integer division. Integer division rounds down. So 1 divided by 3 might result in 0. Well, let's prove that experimentally. What is 1 divided by 3? I'm really curious. 0. Say what? 1 divided by 3 is not 0, but they're both integers, so it does integer division, which means that the answer is also an integer, which means it rounds it down. More strictly speaking, it truncates it, like you said. So in order to make sure it's not doing integer division, I'm going to give it floating point numbers. All right, so it looks like we have 1, 2, 3, 4, 5, 6 places of accuracy for a float, for a 4-bit, for a byte value. But there's one that's 8. So if we did that, a float F1 is equal to 1.0 divided by 3.0, and then we printed it out, we'd get those 6 places. But if we do a double, which is a double wide float, double F2 is equal to 1.0 divided by 3.0, and we print that out, we're going to see twice as many places. So C out F1 followed by a space, followed by F2, followed by EDL, we'll see that F2 can be a lot more precise. It has a lot more digits of precision. Yeah, make a liar out of me. Okay, my gut instinct is to say it's going to be accurate to about 8 places for a float and about 16 places for a decimal. But I couldn't really prove it like that. That was my mistake. I don't know why I'm going into more detail. Y'all are learning more than my other classes previously as I've taught about it. I'm drilling in on this stuff a little bit more. I'm not sure that's a good thing. Okay, so you can use exponential notation to give a value to a float. You could say that this number is equal to 3.14159 E1, which is equal actually to 31.4159. This is kind of implying that 6 places of precision. But you can also force it to be a long double by using a L there. That mystifies me. L has 2 different meanings then. If you suffix a number, an integer with an L, it means make it a long number. But if you add L to a floating point number, it means make it a double. Okay, so I commonly tend, now I won't even say that. You just pick which kind of data type you think you need. If you want a really nice, precise, ultimately precise data type, you'd use a double because it holds, more places, more precision, 16 places of precision as opposed to 8 or whatever the limits are. There's something like that. And doubles can also get much larger. Check it out. The largest value that a float can hold is about 3.4 times 10 to the 38. The largest value that a double can hold is 1.7 to the 308. In other words, 1 followed by 308 zeros. You can hold astronomically large numbers, but only the first 16 places of it are going to be precise, right? But magnitude, the order magnitude is going to be 308. And then the bool data type. We're going to need to stop just running through this, and we're going to need to go back into code again because my eyes are starting to roll up. The bool data type is just true or false, which is stored internally as zeros and ones. And back before C++, just the regular C language didn't have a bool data type, and people used ints or shorts to represent bools, and it was just kind of a gentleman's agreement. If it's a 0, it's a false, and if it's a non-zero, it's a 1. It's a true. So what do you use them for? Flags, like done. Is done equal to true? Is done equal to false? While done equals false, that kind of thing. All right, so I want to veer away from what we're doing right now, and we're going to do a little bit of programming so that we can have a programming assignment. I'm going to make a brand new main because we have a whole bunch of stuff in here that I really don't want. So I'm going to call this one old main, and then I'm going to create a new main, int main, and it needs its system pause down at the bottom of it, system quote pause. Why am I doing this? So that this code won't run. Kind of with a clean slate now. Yeah, we could run it. We could type old main right there, but nah, we're not going to do that. Okay, so what do I want to do? I'm going to write a program that will convert pounds to ounces. I believe there are 16 ounces in a pound. So, OZ is equal to pounds times 16. So we're going to prompt the user for the number of pounds. We're going to calculate and display the number of ounces. That's the first thing we're going to do. So let's pick some variable names and some variable types. To me, OZ and LB is good enough. What data type should we use? Yeah, I'm tending towards float because if you make them ints, then you know they can't type in 2.2 pounds. All they could do is type in 2 pounds. So float OZ, comma, LB, or vice versa. And do we want to give them starting values? There's nothing wrong with initializing them to 0. There's nothing wrong with not initializing them. I'm going to just opt to not initialize them because we're going to fill them in. So we're going to prompt the user for the number of pounds, meaning we need to tell them to type that in. Cout. Man, I hate that that tooltip covers the line of text above it. All right. Cout. How many pounds, question mark, space, end quote. If I put a slash in, they would type in their answer at the beginning of the next line. Since I'm leaving out the slash in, they're going to type in their answer, at the end of this line, which I think is more fun. Okay, and now we need to use a CIN statement to read into OZ. CIN arrow arrow OZ. Now that's enough. We're not going to ask them for the number of ounces. Whoops, I goofed. What's wrong there? Well, that's totally moronic. Why?
It's reading pounds and pounds.
Yeah, I asked for pounds, but then I stored in a variable called LB. All right, now I'm going to run my conversion. I have my formula, so I should be good to go. OZ is equal to LB times 16. And then we can print it out. That equals space, end quote, arrow, arrow, OZ, arrow, arrow, beginning quote, space, ounces, backslash n. And I'm going to run it to see if it works. How many pounds? 10 pounds ought to be 160 ounces. Okay, so that works. Now let's do the reverse. Let's ask for the number of ounces. I should stop and make sure everybody's doing okay. Ask for the number of ounces, convert to pounds, and display it. And the formula is OZ is equal to, no, LB is equal to OZ divided by 16. And y'all can do that while I walk around and make sure that everybody's doing okay. I'm going to do the reverse. I'm going to ask for the number of ounces. I can just reuse my variables. I don't need to redeclare them. Those variables are just as good. So I need to ask for the number of ounces. I need a prompt for it. So how many ounces to convert? Question mark. Space. If you don't put the space there, you'll just have to type in the number right next to the question mark. I think it looks better with the space there. And then CIN, read that into OZ. CIN arrow arrow OZ. Now let's do our conversion. Pound equals OZ times 16. Now let's print that out. Cout. That equals space, end quote, arrow, arrow, LB, arrow, arrow, quote, pounds. All right. Other than the fact that I don't have a space there and this didn't work. 34 to 455, 544. Oh. How about I use division? Alrighty. All right. So we're going to need to make up some homework, but if I make up the homework right now, you'll probably start working on it rather than listening to the rest of the lecture. So we'll wait a little longer before we do it.
Hey, cool question.
Yes, sir.
What does it mean when it says the command is ambiguous?
Good question. Let me come look. Command is ambiguous. Is that what it said?
Yeah.
All righty. Let me come look. The problem our student is getting is that it's complaining the C out on his is ambiguous. Now, it's not on mine, and it's not on many of the others. Let's figure out. Here's the cheap fix for it. STD : : Now it's no longer ambiguous. And we would have to do that for all of them. Why are we having to do that? We had using namespace up here, using namespace STD specifically to avoid having to do that. So I'm sure that somebody else on the planet has asked this question. C out, or C++, C out is ambiguous. I was programming in C++, all of a sudden all the C outs were errors and ambiguous. I can still run the program without errors, but it shows errors on the text, the red scribbly. Closes, it's unclear what you're asking. No, it didn't just happen, you changed something.
Wow.
Yeah, Stack Overflow is by far the best resource for finding programming questions, but the people there are kind of prickly. Alrighty. Nah, I'm not getting it, and I'm not going to spend any more time. If that ever happens to you, if you ever start compiling and it suddenly starts complaining about STD : about C out and CIN being ambiguous, just go ahead and give up and prefix them all with STD : Yeah. Alright, so determining the size of a data type. Say we didn't know how many bytes were in an int. You use the size of function. Well, let's play with that a little bit. Let's ruin our perfectly cute little program. I'm going to go up to the top of main, and I'm going to C out size of 1, 2, 3. Arrow, arrow, ENDL. And then I'm going to see out the size of 1.23. Arrow, arrow, ENDL. Those should both be 4 bytes long. And then let's see out size of, let's make sure that 1, 2, 3 is being treated as a long. So 1, 2, 3, LL. ENDL. Now let's make sure that it's being treated as a double. As a matter of fact, let's create a double and store value in it. So double D is equal to 32. And then see out the size of D. Arrow, arrow, ENDL. And you're probably having to prefix everything with STD : Just copy and paste it. Alright, so my prediction is that since this is an int, ints are 4-byte data types. That should say 4. That one should say 4. A long is 8, so that one should say 8, and so should that one. Nope. 4888. It defied expectation, and this 1.23 was not treated as a float. It's being treated as a double. So, Numeric literals with decimal points are doubles, not floats. I don't know if that's ever going to come and surprise us in the future. In which case, why do you have the LL prefix? It's not necessary. Well, I guess it is if you're typing in something without a decimal point. Okay, anyways. That's what size of is for. Let's do one more. Let's find out what the size of a character is. C out, arrow, arrow, size of, parentheses, single quote, X. Something like that. Arrow, arrow, EDL. And as we expected, a character is just 1 byte. And we could create some shorts and we could create some floats and all the other data types, but that really proves the point. Why would you care about the size? Well, in one specific case, if you have an array of data, an array is a list of bytes, it's a series of elements, you want to calculate the length. In Python, we had cute things like, X is equal to the length of the array, right? You could do that. In Java, you do something similar. C++ has no such nicety. So you have to do size of in order to calculate the length of the array and divide that by the size of each element. Now, we'll certainly talk a lot more about that. But just tuck size of back away in the back of your brain, because in a couple more chapters we'll hit it again. What's the size of a bool? A true or false? It's probably also 1 byte. Why would it take a whole byte? It's just a 0 or 1. You could hold it in 1 bit, right? But the smallest value of information that is shuttled around in memory is byte. Once it's in the chip, it can do extra things with it. I mean, it'll narrow down even further into the individual bits. But like if you issue a read to a disk drive, it's returning a series of bytes and not just a single bit. So anyway, C out, size of the word true. Lowercase in this language, unlike Python. NDL. And that should be a 1 as well. And it is. Okay. Another consequence of this is that if we were going to write all this data out to a file, and we didn't have a nice mechanism for doing so, if we just had to dump raw bytes out, then the first number that we wrote, if we were going to read it back in, we would read four bytes out of it, and we would convert that out. And then to get this number back in, we would read 8 bytes and then convert it to our correct data format. Same for that one. 8, read in another 8 bytes out of our file, another 8. Now that's really primitive. That's more C-style programming than what we would want to do in C++, which is create a stream, an output stream that we could write to using arrows.
It's giving me an error whenever I try to use LL. It's telling me I'm missing a parentheses before the identifier L.
Okay. Did you put a space there?
Yeah.
Okay, that's pretty weird. So the message we're getting is that there should be a parentheses before LL. I'm going to go back and look. Okay, one more thing I want to mention, even though it's not on the slide at this point, I do not believe, is to convert data from one format to the other. You can do casting. Now in Python, you probably used int parentheses to convert something to an int, or you use float parentheses. It's the same way. You could do that. Float f is equal to the float version of 3, right? That's the Python syntax. But there's 2 more syntaxes that C++ gives you. I don't quite know why they give so many different syntaxes. But float g is equal to parentheses, float end parentheses 3. This is whoops, not flog. All right, this is a syntax that you'll see more common. But what it does is it takes that 3 and it converts it to a float. Now, do we have to do that? No, because really the 3 will get converted into a float on the fly when it crosses that equal sign. But there are some data types that you have to use casting in order to get it to do the conversion. Now, for Java, you don't have this syntax. So just tuck that away. And if you feel like, even though you got to use it in Python, you can't use it in Java. So if you feel like memorizing that one, go for it. There's one more weirdo C++ specific syntax, FGH, and it looks like this. It's a more complicated. Static underneath underscore cast angle brace less than float greater than parentheses 3 end parentheses. Now I'm not going to even explain what static cast means, but it does the exact same thing as the prior 2 statements in this case with these simple primitive data types. So I'm usually not going to type in that longer version of it. And we'll hit a section on casting in a later chapter. I just wanted you to see that. So if you need to convert an int to a float or vice versa, so say you have a floating point number and you want to convert it to an int, you can do that. You know, again, that conversion will happen on the fly in C++ because the compiler is loosey-goosey, and it will not happen in Java. So casting, you do a lot more casting in Java programming than you do in C++. Java came out like 15 years after C++, and they kind of tightened up the specifications quite a bit, removed some things, added some things. It's a very similar language though, so they're going to be kind of conflicting in your brain as you learn them both. That just makes it fun. Okay, so we have done determining the size of a data type. This section 2.12 will be the last that we cover today. Variable assignments and initialization. The equal sign is called the assignment operator. That is different from the comparison operator, which is 2 equal signs, the equality operator. If you have an if statement, just like in Python, you use 2 equal signs. If you're copying a value into a variable, you use 1 equal sign. Now what's scary about C++ is it lets you mix them up. The compiler may warn you, but it does let you mix them up, whereas Java will not. So for example, if I did this, not that we've used a lot of if statements but in here, but if I do if f equals 4, do something, I don't know what I'm going to do. Cout wow, comma 4, \n. C++ does not consider that a syntax error. Although there's no, you would never want to do that. Why? Because it's a single equal. So what is it going to do? It's going to erase the contents of f and put a 4 in it. Why would you want to erase the contents of your variable inside of an if statement? The answer is probably 99.9999999% of the time you would not want to. So if we run it, it is going to print wow's 4. But what if you replace that 4 with a 0? You know, we could make it say wow 0 at that point. But it's not going to print that message at all. What's going on there? Remember how underneath it all 0 is treated as a false and non-zero is treated as a true? Well, after this 0 overrides the f, erases and overrides the f, then the result of that expression is 0. So that's a false. So that if statement is false and it will not print that. Anything else other than 0 would cause it to be true. But anyways, that's moronic. You're copying. It's not I'm not saying you're a moron if you make that mistake, because I absolutely have. And trust me, it took me a long time of debugging to figure out what was going on. But the language, in my opinion, should not let you do that. And it does. Let's see if it even gives you a warning message in the output. Hopefully it does. But it may not. Well, it is giving me lots of warnings. It's saying unreferenced local variable. Yeah, that's true. I created all these variables, but I never use them. And here it's telling me that I'm truncating from one value to another. I could go look at line number 115 and find out why that's the case. See, I told you that was wrong. Anyways, okay, so where was I going with that? The assignment operator. Single equal sign copies a value from there to there. The left-hand value, the left-hand side has to be a variable in that case. And the right-hand side is an expression, which could just be a constant, an unnamed constant, a literal, that gets copied into it. And that's called an assignment. If you mix a declaration with an assignment, it's called initializing. So like if we did that, int item, yeah, it is assigning it, but for some reason they're considered slightly different, and that's called initializing. So that'll be the next slide. So you can't mix them up and put the expression on this side and the variable name on this side. Variable initializing is to assign it a value as it is being declared, as it is being defined. You can initialize some or all variables, right? Int length is equal to 12. Great. Comma, width is equal to 5, comma, area. Oh, I guess we're not going to go ahead and initialize area. Why? Because area is going to be calculated on the next line, probably, as being 5 times 12. And then you can use the auto keyword. What does auto mean? Auto means you figure it out. Mr. Compiler, I don't even care what kind of data it is. I just want you to figure it out. I never use the auto keyword, but you could. Like up here where we were creating different variables, I could do auto, Bob is equal to, 1.123. And then auto Sam is equal to 1.23. And auto, Sue is equal to quote 1.23. Completely different data types. And it lets the compiler figure it out. The data type for Bob, according to the compiler, would be an int. The data type for Sam would be a float, and the data type for Sue is a string. I don't see the advantage of doing that.
Is there any way to go in and make it tell you what type you chose?
Good question. In Python, you can call the type method, the type function, and it will tell you what type anything is. I don't know how to get the type, especially if it's a primitive value like that. Let's determining the type of an auto variable in C++. Oh. A, use an IDE. B, don't use auto. Okay, so. All right, here's something that we can do that we haven't demonstrated yet, which is using the debugger. Come over here in this margin and click. Get a red dot there. And then hit the debugger button. What that does is it executes the program up to that point and then stops. Now if we go and hover our cursor over it, we should be able to tell what type these variables are. Yeah, make a liar out of me. You're not going to tell me? Anyways, why would you do that? So you can watch the program run line by line. If I go up to debug, one of the keys will go to the next line. It's called step over. And then it runs that line. And then if I do debug, step over again, it goes to the next line. Now it's kind of tedious having to go up to debug, so you can use the function keys. However, the function keys argue, with your video drivers functions or whatever, if they happen to do those. So it's nice to have the debug bar enabled, which should be enabled. How do you add in additional toolbars? You just right click on one toolbar and you can see all of the toolbars that are available. And so here's the debug toolbar, and I want to keep stepping over, right? And I can watch each one as it has, and I can go and check, the output and watch the output as it executes each line. So eventually it's going to get down to another print statement, how many pounds, and then I click step over again, and it's actually waiting for me to type something because that's what this is, CIN. So I'm going to type in 12, and I hit return, and now the arrow's pointing at the next line. That's where we are. So I'm going to step over again, and then I'm going to click step over again, and it prints out how many ounces it was. This is incredibly important, and in my previous semesters I have not been hammering that in. I ought to make y'all debug something in front of me every single class period, because once you're out in the real world you'll be using a debugger an awful lot. Why? Because you just get into situations where you can't figure out what's going wrong. And there are basically two choices. One is you could litter your entire program with a whole bunch of cout statements trying to figure out how far it got into it, you know. But, you know, a lot of programs don't even print anything like that. So you run it through the debugger, and you can step through line by line watching the variables change. Okay, here we go. My autos, still not showing me. My locals, here we go. I clicked on locals down here in the debugger, and it's telling me that Sam is a double and that Bob was an int and that Sue was a constant character array, which is a form of string, but it's a fixed string, constant character star. Okay, so that's how you tell. You go into the debugger and check it, just like that guy snarkily said. You either use the debugger or you don't use auto. Gotta love Stack Overflow. All right, I think that's about enough, so I need to make some homework for us. I think I already have an assignment that is just about adequate for this purpose. And I'm going to be a jerk and not give you the formulas for the next ones. But if you don't know them, if you can't find them, just text me. If you can Google them and find them, great. I'll prettify it later because it's annoying me. And then convert seconds to minutes, and then convert seconds to hours. So just write code that will do those 6 conversions. Make sense? Alrighty. Might not take you too long, might take you a little bit of time, you know. If you get stuck on any of them, ask me. If you get any weird syntax errors you can't figure out, take a picture, text it to me. So, everybody has my phone number, right? Nobody enrolled late and doesn't have my phone number? It is in the syllabus. Okay, cool. Alrighty, gang, I will see y'all on Monday.
Are you gonna make a Dropbox for you?
Why don't I make a Dropbox? Yeah, excellent idea. I had a nagging feeling.